In March 2025, the James Webb Space Telescope revealed something on Neptune that astronomers had been chasing for more than 30 years. A glow, not reflected sunlight, not a storm. An aurora, shimmering in infrared light on the most distant major planet in the solar system. But the glow was not where anyone expected. Instead of hovering near the poles the way auroras behave on Earth, Neptune's auroras appeared near the planet's mid-latitudes, roughly where South America sits on our world. And when Webb measured the temperature of Neptune's upper atmosphere, the result was staggering. The planet had cooled by hundreds of degrees since the last spacecraft visited. Something is happening at the edge of our solar system that we barely understand, and Webb just caught it glowing. If you enjoy deep dives into discoveries that change how we see the planets around us, a like and a subscribe genuinely help this channel keep going. It means more than you know. Now, get yourself comfortable. Let's begin. The data arrived in the summer of 2023. On the 22nd of June, the James Webb Space Telescope turned its near-infrared spectrograph toward Neptune and collected light from two different hemispheres of the planet, separated by 172 degrees of longitude. Astronomers were not looking for a photograph. They were hunting for a molecule, a specific molecular ion called the trihydrogen cation, known as H3+, that had served as the signature of auroral activity on every other giant planet in the solar system for more than 3 decades. On Jupiter, Saturn, and Uranus, H3+ glows in the near-infrared wherever charged particles streaming outward from the Sun get trapped in a planet's magnetic field, funnel down toward the atmosphere along magnetic field lines, and slam into the hydrogen-rich gas at the top of the atmosphere. The energy from those collisions ionizes the gas, triggers a chain of chemical reactions, and produces H3+. The molecule then radiates at very specific near-infrared wavelengths, creating the telltale auroral glow. It is the fingerprint, the proof that an aurora is happening. And on Neptune, despite years of determined searching with the most powerful ground-based telescopes on Earth, that fingerprint had never been found. Until now, when the Webb data came back and the spectra were processed, the signal was not subtle. Lead author Henrik Mellin, working at the time at the University of Leicester, described being stunned not just by the detection itself, but by the clarity and detail of the signature. The emission line signifying H3+ was extremely prominent, far beyond ambiguity. After more than 30 years of failed attempts with every major infrared facility available to astronomers, the molecule was there, unequivocal, glowing from Neptune's upper atmosphere in wavelengths only Webb could isolate with sufficient precision. And overlaid on an image of the planet, the auroral emission appeared as irregular splotches of infrared light concentrated in regions that would strike any casual observer as deeply intuitively wrong. They were not at the poles. On Earth, the northern lights dance above the Arctic. The southern lights mirror them above Antarctica. This happens because Earth's magnetic field is roughly aligned with its rotation axis, tilted only about 11 degrees from the spin pole. Charged particles from the solar wind get funneled along those field lines toward the magnetic poles, and the upper atmosphere glows where the particles collide with nitrogen and oxygen molecules. The pattern is elegant, roughly symmetric, and intuitive. If you know where the magnetic poles are, you know roughly where to look for the aurora. Most people carry this mental model without even thinking about it. Auroras happen near the poles. That is the rule. Neptune does not follow this rule. Its auroras appeared at geographic mid-latitudes. In the Webb images, the glowing regions sat at positions roughly equivalent to where South America or Southern Africa would be located on Earth. Not near the top of the planet. Not near the bottom. Somewhere in the middle, in a zone that makes no intuitive sense at all unless you understand the invisible architecture operating beneath Neptune's clouds. And what lies beneath is one of the strangest magnetic field configurations in the entire solar system. A field so severely tilted and so dramatically displaced from the center of the planet that it rearranges everything we normally associate with the word aurora. The glow followed the magnetic geometry, not the geographic geometry. And that magnetic geometry, as we are about to see, is unlike anything on any familiar world. But before we follow the magnetic field downward, there is a question that demands answering. Why did it take until 2025 to confirm something that physicists had every reason to expect for more than 30 years? H3+ has been a workhorse molecule in planetary aurora science since the late 1980s. Astronomers first detected it in Jupiter's atmosphere in 1989, and the discovery immediately opened a new window into how giant planets interact with their surrounding space environments. Jupiter's auroras are enormous, hundreds of times brighter than Earth's, and the H3+ glow made them relatively easy to study in the infrared even from ground-based observatories. Saturn followed, then Uranus. Each detection confirmed the same core physics. Energetic particles ride along magnetic field lines, collide with molecular hydrogen in the upper atmosphere, and kick off a series of ion-molecule reactions that produce H3+. The molecule then emits radiation at characteristic near-infrared wavelengths. Point a sufficiently sensitive infrared spectrograph at the right part of the planet, and the aurora reveals itself. Neptune should have been no different. Theoretical models predicted that H3+ should be present. The planet has a confirmed magnetic field, discovered by Voyager 2 during its 1989 flyby. It sits within the solar wind, the constant stream of charged particles flowing outward from the Sun that reaches every planet in the solar system. Its upper atmosphere is hydrogen-dominated, exactly the kind of environment where H3+ forms readily. Every ingredient for auroral production was accounted for, and yet, attempt after determined attempt, using ground-based infrared telescopes, came back empty. Observing teams used some of the most capable instruments in existence, including NASA's Infrared Telescope facility on Mauna Kea in Hawaii, pushing exposure times to their practical limits and stacking observations over multiple nights. They found nothing. Year after year, Neptune refused to cooperate. It became the frustrating outlier, the one giant planet in our solar system that would not show its auroral hand, the missing piece of the puzzle, as multiple astronomers described it. Part of the difficulty is sheer distance. Neptune orbits approximately 30 astronomical units from the Sun, meaning it is 30 times farther from the Sun than Earth is. At that distance, the solar wind is substantially weaker. The ultraviolet flux from the Sun, which is a primary driver of ionization in planetary upper atmospheres, drops enormously. Photoionization, the process by which solar ultraviolet photons strip electrons from atmospheric molecules and help maintain the ionosphere, proceeds at a far lower rate than at closer planets. All of this means Neptune's ionosphere is thinner, less electrically active, and produces fewer H3+ ions than the ionospheres of Jupiter, Saturn, or even Uranus. Webb measured a column-integrated H3+ density at Neptune of approximately 7.2 times 10 to the 14th ions per square meter. That is much smaller than the values observed at any other giant planet. There were simply fewer of these glowing ions to detect. The signal was inherently faint, diluted by distance and by the diminished solar forcing that drives ionospheric chemistry at the edge of the solar system. But distance alone does not fully explain 3 decades of failure. Ground-based telescopes can, in principle, detect even faint infrared signals, if given enough integration time and if the spectral resolution is sufficient to isolate narrow emission lines from broader background signals. The real barrier turned out to be something no one fully appreciated until Webb's spectra revealed it. Neptune's upper atmosphere had changed, dramatically, and that change had dimmed the auroral emission below the detection threshold of every instrument that had tried before Webb. Here is what happened. When Voyager 2 flew past Neptune in August of 1989, it carried instruments that measured the temperature of the planet's upper atmosphere through ultraviolet occultation observations. The value came back at approximately 750 Kelvin, which translates to roughly 477 degrees Celsius. This was the only direct measurement anyone had ever made of Neptune's thermospheric temperature, and it became the anchor point for every subsequent model, every prediction, every observing proposal designed to detect Neptune's auroras. If the upper atmosphere is hot, O3+ molecules vibrate with more energy. They populate higher rotational and vibrational states. They radiate more intensely at their characteristic wavelengths. Models calibrated to that 750 Kelvin temperature predicted detectable emission levels even with ground-based instruments. Observers designed their strategies around those predictions. calculated expected signal-to-noise ratios, and allocated telescope time accordingly. Those predictions were wrong, not because the models were bad, not because Voyager 2 made a measurement error. The 1989 temperature was accurate for 1989, but the atmosphere did not stay at that temperature. Something happened between the flyby and the present day. When the Webb team processed their 2023 spectra and fitted the H3+ emission lines to derive a thermospheric temperature, the number that came back was 358 Kelvin, plus or minus 8. That is barely half of what Voyager 2 recorded. Neptune's upper atmosphere had cooled by approximately 400 degrees in 34 years, roughly 10 Kelvin per year, sustained over more than 3 decades. An ice giant 4.5 billion kilometers from the Sun had lost hundreds of degrees of thermospheric heat on a timescale that, in planetary terms, is an eye blink. Henrik Mellin described being astonished by the result. The temperature in 2023 was just over half of what it had been in 1989. The consequences for auroral detection were immediate and devastating. At lower temperatures, H3+ molecules populate lower energy states and radiate far less energy per ion. The same number of ions at 358 Kelvin produces a vastly fainter glow than the same number at 750 Kelvin. A substantially colder atmosphere results in substantially fainter auroras. This single fact almost certainly explains the entire 3-decade failure. Every prediction of Neptune's auroral brightness was calibrated to a temperature the planet no longer had. Every observer who pointed a telescope at Neptune was searching for a signal that, at the actual atmospheric temperature, was far below their detection limit. They were hunting for the right molecule in the right place using calculations based on conditions that had quietly ceased to exist. This realization does something remarkable. It simultaneously closes one mystery and opens another that may be even more significant. Why did the temperature drop so far, so fast? Neptune's orbital period is approximately 165 Earth years. A single Neptunian season lasts roughly 40 Earth years. The cooling observed between 1989 and 2023 occurred on a timescale shorter than one season. It also occurred on a timescale shorter than the approximately 11-year solar cycle, which modulates the Sun's output of energetic particles and ultraviolet radiation that drive ionospheric heating. If the cooling were caused by seasonal changes in solar illumination angle and atmospheric circulation, you would expect it to unfold over decades to centuries, tracking the slow progression of Neptune's seasons. If it were caused by the solar cycle, you would expect oscillations, periods of cooling followed by warming as the Sun cycles between activity maximum and minimum. Neither pattern fits what the data show. What the data show is a sustained, dramatic decline in temperature on a timescale that does not match any obvious external driver. The Nature Astronomy paper in which these results were published, on March 26 of 2025, stated the situation precisely. The average upper atmosphere temperature is a factor of 2 cooler than the values derived 34 years ago by Voyager 2, showing that the energy balance of this region is regulated by physical processes acting on a timescale shorter than both Neptunian seasons and the solar cycle. That sentence carries enormous weight. It means there is an unknown mechanism governing the thermal state of Neptune's upper atmosphere, a mechanism operating faster than anything we normally invoke to explain temperature changes on giant planets. And we do not yet know what it is. This matters far beyond Neptune. A similar cooling trend, better documented because of more frequent observations over the past several decades, has been measured in the upper atmosphere of Uranus. Both ice giants appear to be losing thermospheric heat at rates that existing models struggle to explain. If the same physical process operates on both worlds, it likely connects to something fundamental about ice giant interiors, magnetospheres, or atmospheric chemistry that current theory is missing. And if the cooling continues, future auroral observations may actually become harder over time, even with Webb's power, because cooler gas produces fainter emission. The window of opportunity for studying Neptune's auroras may not stay open indefinitely. Now consider what the spatial pattern of the detection reveals. The way the auroral emission is distributed across Neptune's disk tells a story about the planet's hidden magnetic architecture. On Earth, the auroral oval traces a roughly circular band around each magnetic pole. On Jupiter, The oval is large, bright, and shaped by interactions with the massive volcanic moon Io. In each case, you can look at where the aurora appears and infer the geometry of the underlying magnetic field. Neptune's auroral emission appeared as irregular, patchy splotches concentrated in the planet's southern hemisphere. The pattern was far from a neat oval. It was asymmetric, diffuse in some regions and concentrated in others, and confined entirely to latitudes far removed from the geographic South Pole. This asymmetry has a clear physical explanation. Neptune's magnetic dipole is not merely tilted 47 degrees from the rotation axis. It is also displaced from the geometric centre of the planet by more than half a Neptune radius, pushed toward the southern hemisphere. This offset means the magnetic field is stronger and more concentrated in the south. The southern magnetic pole sits closer to the planet's surface, creating a smaller, more intense auroral zone where field lines converge into the atmosphere. The northern magnetic pole, being farther from the surface in the opposite hemisphere, produces a larger, more diffuse region where auroral emission is spread over a wider area and is correspondingly harder to detect. Webb's observations captured two different central meridian longitudes, providing views of both hemispheres, and the southern aurora dominated the detection. This is not just a geometric curiosity. The location and shape of the auroral emission encode information about how the solar wind interacts with Neptune's magnetosphere. Because the magnetic axis can swing to extreme orientations relative to the incoming solar wind, as Neptune rotates, the magnetosphere periodically enters a configuration, sometimes described as pole-on, where a magnetic pole faces almost directly into the solar wind flow. This configuration is unique in the solar system. It does not occur at Earth, Jupiter, or Saturn, whose magnetic axes are close enough to their rotation axes that the magnetosphere maintains a more stable orientation. At Neptune, the interaction changes dramatically over a single rotation period of approximately 16 hours. The aurora may brighten, shift, and reshape on timescales of hours, driven by the constantly changing geometry between the magnetic field and the solar wind. Tracking these changes over time would reveal the dynamics of Neptune's magnetosphere in ways that a single snapshot cannot. The technical capability that made all of this possible deserves emphasis. Webb's near-infrared spectrograph, in its integral field unit mode, simultaneously captures spectra across a two-dimensional field of view. This means the instrument does not just point at one spot and record a spectrum. It records a spectrum for every spatial element across the entire visible disk of Neptune. This allowed the team to map exactly where on the planet the H3+ emission was strongest, separating auroral regions from non-auroral regions. It also allowed them to separate the narrow, discrete H3+ emission lines from the broad reflected sunlight spectrum bouncing off clouds lower in the atmosphere. This spectral separation was the technical key that ground-based instruments could not achieve. From the ground, even the best infrared spectrographs operating in the 3 to 5 micrometer range struggled to cleanly distinguish the faint H3+ lines from the reflected solar continuum, especially given telluric absorption, where Earth's own atmosphere absorbs radiation at the same wavelengths H3+ emits. Webb, positioned at the second Lagrange point 1.5 million kilometers from Earth, suffers none of these atmospheric contamination effects. Its 6.5 meter primary mirror collects far more light than any ground-based infrared telescope. Its instruments operate at cryogenic temperatures just a few tens of Kelvin above absolute zero, suppressing thermal noise that would swamp a faint signal. Webb was, in every engineering sense, the machine this detection had been waiting for. Heidi Hammel, the Webb interdisciplinary scientist who led the Guaranteed Time Observation Program, under which the Neptune data were collected, confirmed as much. H3+ had been a clear signifier of auroral activity on all the other giant planets, she noted. The team had expected to find it at Neptune through years of observation, with the best ground-based facilities available. Only with a machine like Webb did they finally get that confirmation. There is something quietly unsettling about the full picture this discovery paints. The most distant major planet in our solar system had been actively producing auroras the entire time. Charged particles from the Sun were reaching Neptune, riding along its distorted magnetic field lines, striking its upper atmosphere, creating H3+, generating an infrared glow. The process never stopped. It was always happening. Every hour of every day, 4.5 billion kilometers from the source of the particles driving it. We simply could not see it because every prediction we relied on was anchored to a thermospheric temperature that had become obsolete, sometime between Voyager 2's departure and the era of modern infrared astronomy. Voyager 2 had hinted at the possibility of auroral activity during its 1989 flyby. Its ultraviolet spectrometer detected diffuse hydrogen emissions on Neptune's night side that were consistent with auroral processes. Its planetary radio astronomy instrument picked up signals suggesting magnetospheric activity, but the data were fragmentary. The flyby lasted hours, not months. The instruments were designed in the 1970s and built for broad survey work, not targeted auroral spectroscopy. There was no infrared spectrograph on Voyager 2 capable of detecting H3+. What the spacecraft saw was suggestive, tantalizing, and incomplete. The hints went into the scientific literature and sat there for more than 3 decades, waiting for a telescope that could follow up. It took 34 years for that follow-up to happen, and when it happened, the result was not simply a confirmation checkbox on a planetary science to-do list. It was a revelation about how rapidly conditions can change on an ice giant at the far reaches of the solar system. A planet that receives roughly 1/900th of the solar energy Earth receives still sustains auroral activity, still responds to the solar wind, and still exhibits dramatic atmospheric temperature shifts on timescales no one anticipated. Neptune is not a frozen relic drifting passively through the outer darkness. It is a world with an active, changing upper atmosphere, a magnetic field that creates auroras in places no textbook diagram would suggest, and an ionosphere that cooled by half in just 3 decades for reasons we cannot yet explain. The question this discovery forces open is not simply what Webb saw, but what the seeing means for the planet hidden beneath the glow. The auroras are a surface symptom, a visible consequence of invisible processes operating deep in Neptune's magnetosphere and far deeper still inside the planet. The tilted, offset magnetic field that places the auroras at mid-latitudes is generated somewhere within Neptune's interior, in a region of exotic, high-pressure chemistry that no instrument has ever directly probed. The cooling of the upper atmosphere connects to the energy balance of the thermosphere, which connects to how energy from the sun, from the interior, and from the magnetosphere all interact at the top of a hydrogen-rich atmosphere, impossibly far from home. Webb did not simply capture Neptune glowing. It exposed the outermost layer of a planetary system that operates according to rules we have not fully written yet. The aurora is the visible symptom, the magnetic field is the engine, the cooling is the unsolved mystery, and all three are tangled together in ways that will require years of continued observation to separate and understand. What comes next goes beneath the glow, into the impossible geometry of the magnetic field that placed those auroras where no one expected, and into the strange substance deep inside Neptune that may explain why the most distant planet carries the most distorted magnetic architecture we have ever measured. Before Webb caught Neptune glowing in infrared, before anyone could map where the auroras formed or measure how cold the upper atmosphere had become, there was a single afternoon of data from a spacecraft already on its way out of the solar system. In August of 1989, Voyager 2 passed through the Neptune system at a velocity of roughly 70,000 kilometers per hour. The encounter lasted mere hours. The spacecraft had already visited Jupiter and Saturn and had executed a flyby of Uranus 3 years earlier. Neptune was its final planetary target. After this, there would be no more worlds to visit. Voyager 2 would continue outward, into the heliosheath, into interstellar space, transmitting data from instruments designed in the 1970s until their nuclear power sources dimmed. But in those few hours near Neptune, the spacecraft carried one instrument that would reshape our understanding of the planet for the next 3.5 decades, a magnetometer. And what it measured was, by the standards of planetary physics, barely believable. The expectation going in was reasonable. Every planet with a significant magnetic field had, to that point, shown a roughly predictable configuration. Earth's magnetic dipole is tilted about 11 degrees from the rotation axis and sits relatively close to the planet's center. Jupiter's dipole is tilted roughly 10 degrees. Saturn's is almost perfectly aligned, less than 1 degree of offset, centered almost exactly on the planet's geometric core. The general pattern seemed clear. Large rotating planets generate magnetic fields through convective motion in their electrically conducting interiors, and those fields tend to be roughly axial, roughly centered, roughly symmetric. There were variations, certainly. Jupiter's field is enormously powerful compared to Earth's. Saturn's is weaker relative to its size. But the basic geometry followed a recognizable template. Neptune shattered that template. The magnetometer aboard Voyager 2 recorded a magnetic field tilted 47 degrees away from the planet's rotation axis. That alone was startling. But the tilt was not even the strangest part. The center of the magnetic dipole, the point from which the field radiates outward, as if from a giant bar magnet, was not located at the geometric center of the planet. It was displaced by 0.55 Neptune radii toward the southern hemisphere, a shift of approximately 13,500 kilometers. To put that displacement in perspective, it is more than the entire diameter of Earth pushed to one side, inside a planet, 4 times Earth's width. The magnetic field of Neptune does not originate from the center of the planet. It originates from a point deep inside the interior that is dramatically off-center, as if the bar magnet generating the field had been shoved sideways and then wrenched at a steep angle relative to the spin axis. Mission scientists at the time were visibly stunned. A maximum magnetic field of nearly 10,000 nanoteslas was measured near closest approach at a distance of just over 1 Neptune radius from the planet's center. Between 4 and 15 Neptune radii outward, the field could be reasonably modeled as an offset tilted dipole, but the fit was imperfect. Higher-order multipolar components were significant, meaning the field was not just tilted and displaced, but also irregularly shaped, with bumps and asymmetries that a simple dipole model could not capture. Neptune's magnetic environment was not merely different from Earth's or Jupiter's. It was fundamentally messier, less organized, less predictable. 3 years earlier, Voyager 2 had encountered something very similar at Uranus. Uranus 2 possesses a magnetic field that is dramatically tilted from its rotation axis by about 59 degrees and offset from the planet's center by roughly a third of the planet's radius. When the Uranus measurements arrived, some scientists speculated that the tilt might be a fluke, perhaps captured during a magnetic field reversal in progress, the way Earth's field periodically flips north and south poles. But when Neptune showed nearly the same bizarre geometry, the fluke hypothesis collapsed. 2 ice giants, observed at different times, at different orbital positions, both displaying wildly tilted and offset magnetic fields. This was not a coincidence. It was a shared characteristic of ice giant interiors. The significance of finding the same pattern on both worlds cannot be overstated. Uranus and Neptune differ in several important ways. Uranus is tipped almost completely on its side, rotating with an axial tilt of about 98 degrees, probably the result of a massive collision early in its history. Neptune's axial tilt is a more moderate 28 degrees. Their distances from the Sun differ by roughly 11 astronomical units. Their internal heat budgets are dramatically different. Uranus radiates almost no excess heat beyond what it absorbs from the Sun, while Neptune radiates more than twice as much energy as it receives. Despite all of these differences, both planets produce magnetic fields that are wildly tilted and offset from their centers. If the explanation was something specific to one planet, the extreme tilt of Uranus, say, or a particular stage of magnetic field reversal, the other planet should not show the same signature. The fact that both do points unmistakably toward a shared cause rooted in what ice giants are made of, not in any accident of orientation or timing. Something about the way these planets are built produces magnetic fields that refuse to behave the way gas giant or terrestrial planet fields do. And whatever that something is, it separates ice giants from every other category of planet we have studied up close. Understanding why requires going deep. Literally deep, thousands of kilometers beneath the cloud tops, into regions of pressure and temperature so extreme that familiar substances stop behaving in familiar ways. On Earth, the magnetic field is generated in the outer core, a layer of liquid iron and nickel, roughly 2,200 kilometers thick, surrounding the solid inner core. Convective currents in this electrically conducting fluid, driven by heat escaping from the inner core, create a self-sustaining dynamo. The fluid motion generates electric currents. The currents generate magnetic fields. The magnetic fields influence the fluid motion, which sustains the currents, which sustain the fields. This feedback loop, called a geodynamo, produces a field that is roughly dipolar and roughly centered because the convection occurs in a deep, thick, roughly symmetric shell around the planet's center. Jupiter and Saturn follow a similar principle, except the electrically conducting fluid is metallic hydrogen. At the tremendous pressures inside these gas giants, hydrogen is compressed so tightly that its electrons become delocalized, flowing freely the way electrons flow in a metal. This metallic hydrogen layer is deep and extensive, occupying much of the planetary interior. The resulting dynamo produces strong, roughly centered, roughly axial magnetic fields consistent with what Voyager and later spacecraft measured. Neptune and Uranus are different. They are not gas giants. They are ice giants. Their interiors are not dominated by hydrogen and helium compressed to metallic states. Instead, beneath a relatively thin hydrogen-helium atmosphere lies a vast mantle composed primarily of water, methane, and ammonia at pressures reaching millions of times the atmospheric pressure at Earth's surface and temperatures of thousands of Kelvin. This mantle is not ice in any everyday sense. It is a hot, dense, supercritical fluid under pressures so extreme that the molecular structure of water itself transforms into something alien. This is where a remarkable piece of recent science connects directly to the Aurora web detected 4.5 billion kilometers away. In 2026, a paper published in Nature reported the results of laboratory experiments that subjected ordinary water to pressures exceeding 1.5 million times the pressure at Earth's sea level and temperatures around 2500 Kelvin. Under these conditions, water enters a state known as superionic water. In this phase, oxygen atoms lock into a rigid crystalline lattice, forming a solid framework. But the hydrogen atoms do not lock in place. They become ionized, shedding their electrons, and flow freely through the oxygen lattice like a liquid moving through a fixed scaffolding. These mobile hydrogen ions carry electric current. The result is a material that is simultaneously a solid and a conductor, a strange hybrid state that exists only under the crushing conditions found inside ice giant interiors. The crucial finding was not just that superionic water exists, it was that the crystal structure of the oxygen lattice matters enormously for the magnetic field it produces. If the lattice were perfectly ordered, a single uniform crystal with hydrogen ions flowing smoothly through it, the resulting electrical currents would generate a relatively clean, symmetric magnetic field. But the experiments showed that under realistic planetary conditions, the lattice is not perfectly ordered. It is riddled with defects. Different stacking patterns of the crystal layers coexist in a disordered mixture. This disorder disrupts the flow of hydrogen ions, creating irregular asymmetric current patterns. And those irregular currents naturally produce a magnetic field that is tilted, offset, and multipolar. In other words, the bizarre magnetic fields of Neptune and Uranus may be a direct, inevitable consequence of the material generating them. The dynamo inside an ice giant does not operate in a deep shell of metallic hydrogen like Jupiter's. It operates in a shallower, more irregularly structured layer of superionic water, where disorder in the crystal lattice maps directly onto disorder in the resulting magnetic field. The tilted, offset dipole that Voyager 2 measured at Neptune in 1989 may be a fingerprint of the microscopic structure of exotic water, thousands of kilometers beneath the cloud tops. This connection between laboratory physics and planetary-scale magnetic architecture is still being refined. The experiments cannot perfectly replicate the exact pressures, temperatures, and chemical mixtures present inside Neptune, where the mantle is not pure water but a complex cocktail of water, methane, ammonia, and other compounds under conditions that vary continuously with depth. But the fundamental insight holds. The type of conducting material inside a planet determines the geometry of the magnetic field it produces, and the conducting material inside Neptune is not a well-behaved metallic fluid. It is a strange, partially crystalline, partially liquid, structurally disordered exotic phase of water. The messiness of the material produces the messiness of the field. Now bring the magnetic field back to the surface, back to the atmosphere, back to the Aurora's web detected. The 47-degree tilt and the half-radius offset do not just create an abstract geometric puzzle for theorists. They reshape the entire interaction between Neptune and the solar wind in ways that have real, observable consequences. The solar wind at Neptune's distance is not the dense, fast-flowing particle stream that batters the inner planets. At 30 astronomical units from the Sun, the wind has spread across an enormous volume of space. Its density is far lower. Its dynamic pressure is weaker. The magnetic field embedded in the solar wind, called the interplanetary magnetic field, is correspondingly attenuated. Neptune's magnetosphere, the bubble of space dominated by the planet's own magnetic field, sits in a calmer, thinner medium than Earth's or Jupiter's. The bow shock, where the solar wind first encounters Neptune's magnetosphere, was detected by Voyager 2 at approximately 35 Neptune radii upstream, and the magnetopause boundary, where the planet's field begins to dominate, was tentatively identified at roughly 26.5 Neptune radii. But what makes Neptune's magnetosphere truly unusual is not its size or strength. It is the way it rotates. Neptune spins on its axis once every approximately 16 hours. Because the magnetic axis is tilted 47 degrees from the rotation axis, the orientation of the magnetosphere relative to the incoming solar wind changes continuously as the planet turns. During some phases of rotation, the magnetic axis points roughly toward or away from the Sun, creating the pole-on configuration that researchers have identified as unique to the ice giants. In this geometry, one magnetic pole faces almost directly into the solar wind. Charged particles can flow more or less straight down the magnetic field lines into the atmosphere, potentially creating intense auroral emission in a concentrated region. During other phases, the magnetic axis is oriented more sideways relative to the solar wind, spreading the interaction over a wider area and reducing the intensity at any single point. This means Neptune's aurora is almost certainly not static. It does not sit in one place with one brightness, the way a textbook diagram might suggest. It breathes, it shifts. Every 16 hours, the magnetic geometry rotates through a full cycle of orientations relative to the solar wind, and the auroral pattern should respond accordingly, brightening, dimming, migrating across the disk. Webb's 2023 observations captured two different central meridian longitudes, separated by about half a rotation, providing a glimpse of this variability. But a full characterization would require continuous monitoring over multiple rotation periods, watching the auroral pattern evolve in real time as the tilted dipole swings around. The offset adds another layer of complexity. Because the magnetic dipole center is displaced toward the southern hemisphere, the southern magnetic pole sits closer to the planet's physical surface than the northern pole does. Field lines converge more steeply and over a smaller area in the south. This concentrates the flux of incoming charged particles into a tighter zone, producing a smaller but potentially brighter southern auroral region. The northern magnetic pole, being farther from the surface on the opposite side, creates a broader, more diffuse region where particles spread out before reaching the atmosphere. The auroral brightness per unit area is lower in the north, even if the total energy input is comparable. This asymmetry was visible in the Webb data, where the southern auroral emission was more prominent. But energetic particles have to get to the atmosphere before any of this matters, and at Neptune's distance, the question of where those particles come from is not as straightforward as it might seem. On Earth, the primary driver of auroral activity is the solar wind interacting with the magnetosphere through a process called magnetic reconnection, where the interplanetary magnetic field merges with the planetary field, allowing solar wind particles to penetrate the magnetosphere and accelerate along field lines into the polar atmosphere. On Jupiter, the dominant driver is different. Jupiter's powerful magnetic field sweeps up material from the volcanic moon Io and accelerates it to extreme energies, creating an internally driven magnetosphere where auroral brightness correlates more with the planet's own rotation than with solar wind conditions. Neptune likely occupies a middle ground. It has no equivalent of Io, no massive volcanic moon constantly injecting material into the magnetosphere. Its moons are too small and too distant from the main magnetic field to significantly load the magnetosphere with plasma. So the solar wind is probably the primary external source of energetic particles. But Neptune's internal magnetospheric dynamics matter too. The rapid rotation of the tilted offset dipole drives electric currents in the magnetosphere that can accelerate particles independently of the solar wind. The relative importance of solar-driven versus internally driven processes is one of the key questions that future observations and future missions will need to answer. This brings us back to the temperature mystery, because the upper atmosphere where the auroras form is the same region that has cooled so dramatically since Voyager 2's visit. The thermosphere and the ionosphere overlap at Neptune. The region where Ha3+ is produced by auroral particle impacts is the same region whose temperature dropped from approximately 750 Kelvin to 358 Kelvin. And the temperature of the ionosphere determines how efficiently it radiates energy, how quickly H3+ molecules lose their excitation, and how brightly the aurora glows. But here is what makes the cooling doubly strange. The 750 Kelvin temperature Voyager 2, measured in 1989, was itself a puzzle. Not because it was wrong, but because it was too high. This is part of a much older problem in planetary science that predates Webb by decades, sometimes called the giant planet energy crisis. On every giant planet we have measured, the upper atmosphere is far hotter than solar ultraviolet heating alone can explain. Jupiter's thermosphere sits at roughly 700 Kelvin. Saturn's is around 500 Kelvin. Uranus was measured at roughly 750 Kelvin during the Voyager 2 flyby in 1986, and Neptune came in at a comparable 750 Kelvin in 1989. In every case, models that account only for the sun's ultraviolet radiation as the heat source predict thermospheric temperatures of just 100 to 200 Kelvin. Something else is pumping energy into the upper atmospheres of all four giant planets, and after decades of investigation, there is still no consensus on what that something is. Candidate explanations include gravity waves propagating upward from deeper atmospheric layers, breaking in the thermosphere and depositing their energy as heat. Magnetospheric interactions, including auroral particle bombardment, contribute on planets with strong magnetic fields and active magnetospheres. Redistribution of heat from the auroral zones to lower latitudes by thermospheric winds has been proposed at Jupiter, but remains difficult to model accurately. Some researchers have suggested that chemical heating from the recombination of ions and electrons in the ionosphere could contribute. Others point to the dissipation of acoustic waves or interactions between the magnetic field and atmospheric tides. None of these mechanisms, alone or in combination, has been conclusively shown to produce the observed temperatures on all four planets. The energy crisis remains open. Neptune's Voyager-era temperature of 750 Kelvin fit neatly within this broader puzzle. It was anomalously hot in the same way Jupiter and Saturn and Uranus are anomalously hot, but Webb's measurement of 358 Kelvin changes the picture. Neptune's thermosphere has not just cooled, it has cooled to a point much closer to what solar ultraviolet models actually predict. In a sense, the mystery has inverted. The question used to be, why is Neptune's upper atmosphere so hot? Now the question is, why was it so hot in 1989, and what turned off the extra heating? Or, alternatively, did Neptune's thermosphere spend most of its time near 358 Kelvin, with the Voyager-era temperature representing an unusual warm spike rather than the normal state? This reframing has implications for every giant planet. If the extra heating on Neptune turns out to be intermittent, switching on and off on timescales of decades, then the energy crisis may not require a constant background mechanism operating at all times. It may instead involve episodic processes tied to solar activity, magnetospheric reconfigurations, or internal atmospheric dynamics that vary over timescales we have not been monitoring long enough to characterize. The same could be true at Uranus, where a well-documented cooling trend has been tracked over the past 3 decades using ground-based infrared observations. Perhaps the giant planet energy crisis is not about finding one missing heat source. Perhaps it is about understanding a variable heating process that pulses on and off, and we happen to catch Neptune during a warm phase in 1989 and a cool phase in 2023. Testing this idea would require exactly what it sounds like: sustained, repeated thermospheric temperature measurements on all 4 giant planets over decades, using instruments sensitive enough to track H3+ emission and derive temperatures to within a few tens of Kelvin. Webb can do this for individual observations, but the cadence and duration required to characterize variability over multiple solar cycles and multiple planetary seasons goes beyond what any single telescope allocation can deliver. It requires a programmatic commitment to ice giant atmospheric science that does not yet exist. The energy balance of the upper atmosphere is a puzzle within a puzzle. Heat enters from multiple sources. Solar extreme ultraviolet radiation deposits energy by ionizing atmospheric molecules. The solar wind delivers energy through magnetospheric coupling. Internal heat from the planet's deep interior conducts upward through the atmosphere, and auroral particle bombardment directly heats the gas where energetic particles collide with neutral molecules. Heat leaves the upper atmosphere primarily through infrared radiation, much of it carried by the very H3+ molecules that serve as the auroral tracer. H3+ is an extremely efficient radiator. It acts as a thermostat for giant planet upper atmospheres, cooling the gas by emitting infrared photons that escape to space. The balance between these heating and cooling mechanisms determines the thermospheric temperature. If heating increases, the temperature rises. If cooling becomes more efficient or heating decreases, the temperature falls. A drop from 750 to 358 Kelvin implies that the net energy input to Neptune's upper atmosphere decreased substantially between 1989 and 2023, or that the cooling efficiency increased, or some combination of both. One possibility is that the solar wind was more active during the Voyager 2 encounter than during the Webb observations, delivering more energy to the magnetosphere and upper atmosphere. The Sun goes through approximately 11-year cycles of activity, and Voyager 2's flyby occurred during a period of moderate to high solar activity. If the 2023 observations happen to coincide with lower solar activity, the reduced energy input could partially explain the temperature drop. But the magnitude of the cooling, a factor of 2, is far larger than what solar cycle variations alone can plausibly produce. Solar cycle effects typically modulate thermospheric temperatures by tens of percent, not by 50%. Another possibility is that the cooling is connected to Neptune's seasons. Neptune's axial tilt is approximately 28 degrees, comparable to Earth's, so it does experience seasons, but each season lasts roughly 40 Earth years. Changes in the angle at which sunlight strikes the upper atmosphere over a Neptunian season could alter the distribution of solar heating and the pattern of atmospheric circulation, potentially affecting thermospheric temperatures, but the timescale still does not fit cleanly. 34 years is less than one full Neptunian season, and the cooling rate, roughly 10 Kelvin per year sustained over 3 decades, suggests something more systematic than a gradual seasonal drift. A third possibility, and the one that may ultimately prove most important, is that the cooling is driven by changes in the magnetospheric energy input itself. If Neptune's magnetosphere has undergone a long-term reconfiguration, perhaps driven by gradual changes in the solar wind conditions at 30 astronomical units as the Sun's overall activity has evolved, the amount of auroral heating deposited in the upper atmosphere could have decreased steadily. This would be consistent with fainter auroras, lower H3+ emission, and cooler thermospheric temperatures. It would also mean the aurora web detected in 2023 is not Neptune's typical state, but rather a quiet period baseline, and that the auroral display Voyager 2 hinted at in 1989 may have been significantly brighter. Testing these hypotheses requires exactly what astronomers have proposed: monitoring Neptune with Webb over a full solar cycle to see whether the thermospheric temperature and auroral brightness vary with solar activity. If the temperature rises during the next solar maximum, the solar wind-driven explanation gains strength. If it continues to decline regardless of solar cycle phase, something deeper and less understood is at work. The magnetic field, the auroras, the cooling, and the exotic interior are not separate stories. They are layers of the same story. Superionic water deep inside the planet generates a disordered, tilted, offset magnetic field. That field reaches outward into space, catches charged particles from the solar wind, and funnels them into the upper atmosphere, at latitudes that make no sense by earthly standards. The particles excite H3+, which glows in the infrared and simultaneously radiates heat away from the atmosphere. The balance between particle energy coming in and infrared energy going out sets the temperature. And the temperature has been dropping for reasons that currently elude explanation. Every piece of this system is connected to every other piece through physics that operates across scales, ranging from the crystal lattice of water molecules at millions of atmospheres of pressure to the sweeping interaction between a planetary magnetosphere and the solar wind across tens of planetary radii. Webb's detection of the aurora was not the end of the investigation. It was the moment the investigation finally became possible. For the first time, astronomers have a direct tracer of magnetospheric activity on Neptune, a molecule whose brightness and spatial distribution encode information about magnetic field geometry, particle precipitation, and atmospheric temperature all at once. Every future observation that detects H3+ on Neptune will add another data point to the emerging picture of how this planet's magnetic engine operates and how the upper atmosphere it powers has been changing. But before we follow the story deeper into the ice giant mystery that connects Neptune's magnetic field to the broader population of planets in our galaxy, there is another dimension of the Webb-Neptune story that has been waiting. The auroras were detected in 2025, but Webb first looked at Neptune in 2022, and what it saw then was not a glow, it was a disappearance. The familiar blue planet of every textbook and classroom poster vanished in near-infrared light, replaced by something darker, stranger, and ringed with structures that had not been seen in over 3 decades. The same telescope that revealed the hidden auroras had already been quietly dismantling the most basic visual assumption people carry about the 8th planet. And that earlier view of Neptune, now seen in the context of the aurora discovery, carries a weight it did not carry before. Before the auroras were detected, before the thermospheric temperature shocked anyone, Webb had already done something to Neptune that no telescope had done before. It had taken the blue away. On the 12th of July, 2022, Webb pointed its near-infrared camera at Neptune and captured an image that was released to the public 2 months later, in September of that year. The response was immediate and disorienting. People who had grown up with the Voyager-era photograph of a vivid cerulean sphere framed against the darkness of the outer solar system suddenly found themselves looking at a planet they did not recognize. Neptune was dark, almost ghostly. The brilliant blue that had defined the planet in every textbook, every poster, every documentary was gone. In its place was a dim, grey-toned disk, surrounded by unexpectedly crisp structures that gleamed against the blackness of space. The planet that had been the blue jewel at the edge of the solar system had become something closer to a shadow of itself, haunted by rings that had not been seen this clearly in more than 30 years. The reason for the transformation is straightforward physics, but the visual impact is profound. Neptune appears blue in visible light because methane in its atmosphere absorbs red wavelengths and reflects blue ones back to the observer. This is the version of Neptune that human eyes see, the version Voyager 2 photographed, the version that became iconic. But Webb's near-infrared camera operates in wavelengths between 0.6 and 5 micrometers, well into the near-infrared range where methane absorption is even more aggressive. At these wavelengths, methane does not just absorb red light, it absorbs almost everything. The atmosphere becomes nearly opaque. Sunlight that enters Neptune's atmosphere at near-infrared wavelengths gets swallowed before it can bounce back to the telescope. The result is a planet that appears profoundly dark across most of its disk, a world whose atmosphere has effectively become a light trap in the infrared. But that darkness is not featureless. It is precisely because the bulk of the atmosphere absorbs so strongly that certain structures stand out with startling clarity. Anything sitting above the main methane layer, high enough in the atmosphere that sunlight reflects off it before being absorbed, appears as a bright feature against the dark disk. And Webb found several. The most visually striking features were high-altitude methane ice clouds. These appeared as brilliant streaks and spots scattered across Neptune's disk, concentrated particularly in the southern hemisphere. They are clouds made of methane ice crystals that form at altitudes above most of the atmospheric methane. Sunlight hits them first, bounces back toward the observer, and escapes before the methane below can absorb it. In visible light, these clouds are present but overwhelmed by the overall blue glow of the atmosphere. In Webb's near-infrared view, they pop. They become the brightest features on the planet itself. isolated beacons of reflected light floating above an otherwise dark world. These cloud features are not static. Observations from the Hubble Space Telescope and the Keck Observatory over previous years had tracked similar high-altitude clouds evolving rapidly, appearing, shifting, and dissipating over days to weeks. Nobody fully understands what drives them. Their behavior has been compared to cirrus clouds on Earth, but the comparison is limited. They form in an atmosphere with wind speeds approaching 2,000 kilometers per hour, far faster than any winds on Earth, in conditions so cold that methane itself freezes into ice crystals. Their appearance in Webb's images confirmed that Neptune's atmosphere was still producing these transient, high-altitude cloud features decades after Voyager 2 first photographed similar storms. But the clouds were not the only atmospheric feature Webb revealed. A thin line of brightness circled the planet's equator, subtle but unmistakable. This equatorial band is thought to be a signature of Neptune's global atmospheric circulation. The prevailing model suggests that at the equator, atmospheric gas descends from higher altitudes, compresses, and warms. Warmer gas emits more strongly at infrared wavelengths than the cooler gas surrounding it. The result is a faint glow tracing the equatorial zone, a thermal signature of atmospheric dynamics rendered visible only because Webb's infrared sensitivity could pick it out against the dark methane-absorbed background. In visible light, this feature is invisible, buried under the uniform blue glare. In the infrared, it becomes a line drawn around the planet's middle, evidence that the atmosphere circulates on a global scale, even at 30 times Earth's distance from the Sun. Near the South Pole, Webb resolved something that had been known from earlier observations but never seen this clearly. A continuous band of high-latitude clouds surrounded a previously identified vortex at Neptune's southern pole. Polar vortices are common on giant planets. Jupiter and Saturn both possess them, driven by the dynamics of rapidly rotating atmospheres. Neptune's southern polar vortex had been detected before, but the surrounding cloud structure was poorly characterized. Webb's image showed a coherent ring of cloud activity encircling the vortex, hinting at organized atmospheric circulation near the pole that connects to the broader pattern of winds and storms operating across the entire planet. The infrared features Webb revealed were new, but the violence in Neptune's atmosphere was not. Even in visible light, even with instruments far less capable than Webb, Neptune had been showing signs of dramatic atmospheric activity for decades. Voyager 2's most famous Neptune photograph captured a massive dark storm in the southern hemisphere called the Great Dark Spot. It was an anticyclonic vortex roughly the size of Earth, visually reminiscent of Jupiter's Great Red Spot, though the resemblance was superficial. The winds around the Great Dark Spot reached speeds estimated at 2,100 kilometers per hour, the fastest atmospheric winds measured on any planet. Bright companion clouds of methane ice hovered at the storm's edge, pushed upward by the circulation pattern around the vortex. But when the Hubble Space Telescope pointed at Neptune in 1994, just 5 years after Voyager 2's flyby, the Great Dark Spot was gone. It had vanished entirely. No trace remained in the southern hemisphere where it had dominated the planet's visible appearance. This was a shock. Jupiter's Great Red Spot has persisted for centuries, possibly longer. The expectation was that a comparable storm on Neptune might show similar longevity. Instead, it evaporated in less than 5 years. Then, almost immediately, Hubble spotted a new dark storm forming in Neptune's northern hemisphere. The planet had not become calm. It had simply destroyed one storm and started building another, as if the atmosphere treated planet-sized vortices as disposable, temporary features in a relentless cycle of creation and destruction. In the decades since, Hubble and ground-based observatories have tracked multiple dark storms appearing and vanishing on Neptune. Some lasted a few years, others faded within months. Each time, bright companion clouds accompanied the dark vortex, marking its position and hinting at the extreme vertical circulation patterns driving the storm. In 2018, Hubble caught a dark storm in the act of drifting toward the equator, where models predicted it would break apart. It did, spectacularly, shedding companion clouds as it disintegrated. The atmosphere of Neptune, despite receiving barely 1/900th of the solar energy Earth receives, produces and destroys weather systems on scales that dwarf any terrestrial hurricane. The energy driving this activity comes not from the Sun, but from Neptune's own interior. The planet radiates more than 2.5 times as much energy as it absorbs from sunlight, and that internal heat engine powers an atmosphere of astonishing ferocity. Webb's infrared view added a new layer on top of this already violent picture. The high-altitude methane ice clouds, the equatorial circulation band, and the polar vortex structure are infrared features invisible to the instruments that tracked the dark storms. They represent a different altitude regime, a different set of physical processes, and a different way of seeing the same restless atmosphere. Neptune was already known to be one of the most dynamically active planets in the solar system. Webb showed that the activity extends to altitudes and wavelength ranges that earlier instruments could not access. The planet is not merely violent, it is violent across multiple atmospheric layers simultaneously, in ways that become visible only when you look in the right part of the electromagnetic spectrum. All of these atmospheric features are significant, but the element of the 2022 Webb image that reshaped how people think about the Neptune system was not on the planet itself. It was the rings. Most people, if asked which planet has rings, would say Saturn. Some would add Uranus. A few might recall that Jupiter possesses a faint ring system. Almost no one thinks of Neptune as a ringed planet, despite the fact that its rings have been known since the 1984 stellar occultation observations that detected incomplete ring arcs, and were fully confirmed by Voyager 2 during the 1989 flyby. Neptune's rings are thin, faint, and composed of particles that are dark and difficult to observe. In the decades after Voyager 2's departure, ground-based observations and even the Hubble Space Telescope struggled to image them. The rings faded from public awareness. They became a footnote rather than a feature. Webb changed that in a single image. The near-infrared camera captured several bright, narrow rings with clarity that astronomers had not seen since Voyager 2 flew past more than 3 decades earlier. The main rings stood out crisply against the dark disk and the black background of space. Their structure was resolved with enough detail to trace variations in brightness along their length, hinting at the distribution of ring particles and the dynamics that maintain them. Heidi Hammel, who has studied Neptune's system for decades, described the ring system in the Webb image as absolutely mind-boggling, noting she had not seen that level of detail since the Voyager encounter. But Webb did not just see the bright rings. It also detected something fainter, and in some ways more scientifically important. Between the main rings, the image revealed Neptune's dust bands, diffuse sheets of tiny particles spread through the ring plane. These dust bands had not been seen in the infrared before. They are composed of micrometer-scale particles, far smaller than the chunks of ice and rock that make up the main rings, and they are thought to be produced by micrometeorite impacts on larger ring particles and on small moonlets embedded within the ring system. The dust scatters infrared light differently than larger particles, and Webb's extraordinary stability and precision allowed it to detect the faint infrared signature of these bands against the overwhelming darkness of the surrounding space. The rings are more reflective in the infrared than in visible light, which is one reason they stood out so dramatically in the Webb image. This increased reflectivity makes infrared observation the preferred method for studying ring composition and structure, and it explains why Webb succeeded where decades of visible light observation had been limited. The rings appear to consist primarily of dark, carbon-rich material mixed with ice, though the precise composition remains poorly constrained. A dedicated orbiter with instruments designed for ring science would be needed to determine exactly what Neptune's rings are made of, how they formed, and how long they will persist. The ring system itself is a reminder that Neptune is not a solitary object drifting through the outer darkness. It is the hub of a complex system of rings, moonlets, and moons that interact gravitationally in ways that shape the structure of the ring plane. Some of Neptune's small inner moons orbit among the rings, and their gravitational influence sculpts ring edges and confines ring material into narrow bands. The relationship between moons and rings is dynamic. Ring particles are constantly being created through collisions and destroyed through various processes, and the gravitational shepherding of small moons maintains the system in a state of ongoing equilibrium that astronomers are still working to understand. And then there was Triton. In the wider field version of the 2022 Webb image, which captured Neptune and its surrounding environment, rather than just the planet's close-up disk, one object dominated everything, a point of light far brighter than Neptune itself, blazing in the upper portion of the image with the characteristic diffraction spikes that Webb's hexagonal mirror segments produce around bright point sources. It looked like a star. It was not. It was Triton, Neptune's largest moon, and in infrared light it outshone the planet it orbits by a dramatic margin. The reason is surface composition. Triton is coated in frozen nitrogen ice, and that ice reflects approximately 70% of the sunlight that hits it. In the near-infrared wavelengths where methane absorbs light from Neptune's atmosphere and makes the planet appear dark, Triton's nitrogen ice remains highly reflective. The moon becomes a mirror in a wavelength range where the planet becomes a shadow. The contrast is visually startling and scientifically informative. It reveals just how different the surfaces and atmospheres of these two objects are. Even though they occupy the same region of the outer solar system and receive the same feeble illumination from the distant sun, Triton is not an ordinary moon. It orbits Neptune in a retrograde direction, meaning it moves opposite to the planet's rotation. No other large moon in the solar system does this. Retrograde orbits are a hallmark of captured objects, rather than moons that formed in place alongside their parent planet. The leading hypothesis, supported by decades of dynamical modeling, is that Triton originated as a Kuiper belt object, a body from the vast population of icy worlds beyond Neptune's orbit, and was gravitationally captured by Neptune at some point in the planet's history. The capture was almost certainly catastrophic for whatever moon system Neptune originally possessed. Triton is massive. Its diameter is approximately 2,700 kilometers, making it larger than the dwarf planet Pluto. When an object this large enters a planetary system on a capture trajectory, its gravitational influence disrupts the orbits of any pre-existing moons. Computer simulations suggest that Triton's capture scattered or destroyed Neptune's original satellite system, and that the small inner moons we observe today, the ones that orbit close to the planet among the rings, are not survivors. They are second-generation objects that reaccreted from the debris disk left behind after Triton's arrival through the original system into chaos. This makes Neptune's current moon system a forensic scene. The 7 inner regular moons, including Proteus, the second largest at roughly 420 kilometers across, orbit close to the equatorial plane in circular, prograde orbits. They are the rebuilt system, assembled from rubble. Beyond Triton, Neptune has 8 known outer irregular moons with distant, eccentric, inclined orbits. Some are prograde, some retrograde. Their orbital groupings suggest they are fragments of larger parent moons that were shattered by collisions with comets or asteroids, leaving clusters of debris in similar orbits. 2 of these outer moons, provisionally designated S2021, N1, and S2000, 2N5, they were discovered as recently as 2021 using the Subaru telescope and announced in 2024, bringing Neptune's total known moon count to 16. Neptune's moon system is not just a collection of orbiting objects, it is a record of violence. The capture of Triton rewrote the entire system. The inner moons are fragments reassembled from destruction. The outer irregular moons are shrapnel from later collisions. Triton itself, now settled into a nearly circular retrograde orbit after billions of years of tidal evolution, carries on its surface the marks of its Kuiper belt origins. And those marks are extraordinary. Voyager 2 observed nitrogen geysers erupting from Triton's surface during the 1989 flyby, shooting plumes of dark material 8 kilometers into the thin atmosphere. These are not water geysers like those on Saturn's moon Enceladus. They are driven by a different mechanism. The leading explanation involves solar heating of subsurface nitrogen ice through Triton's translucent surface layer. As sunlight penetrates the surface and warms trapped nitrogen below, the gas pressure builds until it fractures the overlying ice and erupts in a plume. The dark streaks left behind by these eruptions were visible in Voyager 2 images, trailing downwind across Triton's frozen plains, marking the surface with evidence of ongoing geological activity at a temperature of roughly 38 Kelvin, minus 235 degrees Celsius. A world that cold should be geologically dead by any intuitive reckoning. It is not. The surface itself defies simple description. Voyager 2 photographed a terrain unlike anything seen elsewhere in the solar system, a crumpled, bumpy texture that mission scientists nicknamed cantaloupe terrain because of its resemblance to the skin of a cantaloupe melon. The origin of this texture remains debated. Some models suggest it formed through diaporism, a process where less dense material rises through denser material in a series of convective plumes, deforming the surface from below. Others propose it resulted from tidal stresses during the circularization of Triton's orbit after capture. Whatever the cause, it points to a geologically complex history that a single flyby could only begin to document. Perhaps the most tantalizing aspect of Triton's geology is what it implies about the interior. When Triton was first captured by Neptune, its orbit would have been highly eccentric, looping far out and then swinging close to the planet. Over billions of years, tidal forces between Neptune and Triton gradually circularized the orbit, converting orbital energy into internal heat through tidal flexing of Triton's interior. This tidal heating would have been enormous during the early stages of orbit circularization, enough to melt much of the Moon's interior and maintain a global subsurface ocean of liquid water beneath the frozen surface. The question is whether enough tidal heating persists today to keep some portion of that ocean liquid. Triton's orbit is now nearly circular, which reduces tidal flexing. But some models suggest that small residual eccentricities, combined with radiogenic heating from the decay of radioactive elements in Triton's rocky core, could maintain a thin liquid water layer even now. If a subsurface ocean exists on Triton, it places this captured moon alongside Europa and Enceladus on the short list of solar system worlds where liquid water may persist beneath an icy shell. And wherever liquid water persists in contact with a rocky interior, the conditions for prebiotic chemistry may exist. Triton would not be the most accessible ocean world to study. It is far more distant than Europa or Enceladus, and any mission to investigate it would need to travel to the Neptune system first. But the scientific interest is immense, because Triton is not just a possible ocean world, it is a possible ocean world that originated in the Kuiper Belt, was captured into a planetary system, and underwent billions of years of tidal evolution. Its story connects the chemistry of the outer solar system to the gravitational dynamics of planetary capture, to the potential habitability of icy moons in ways that no other single object can match. Webb's 2022 image of Triton, blazing above the darkened disk of Neptune, captured all of this history in a single frame. The brightest object in the image is an interloper, a world stolen from the Kuiper Belt that destroyed and rebuilt the system it now dominates. Its reflective nitrogen surface outshines the methane-darkened planet below. The quiet beauty of the image conceals one of the most violent and geologically rich histories in the outer solar system. 7 of Neptune's 16 known moons were visible in the wider field Webb image. The others were either too faint, too close to the planet's glare, or positioned outside the camera's field of view. But even the moons that were visible appeared as faint dots, easily overlooked next to Triton's brilliance and the ring's delicate tracery. The Neptune system in infrared light is a study in contrasts. A dark planet, bright ice clouds, crisp rings, faint dust bands, a blinding captured moon, and scattered through the frame, the dim points of smaller moons whose orbits carry the scars of a catastrophe billions of years old. Now, step back and consider what Webb accomplished across these two sets of observations: the 2022 near-infrared camera images and the 2023 near-infrared spectrograph data that revealed the auroras in 2025. Taken together, they do not simply add detail to an existing picture of Neptune, they replace the picture entirely. Before Webb, the dominant image of Neptune in the public imagination, and to a significant extent in the scientific imagination, was the Voyager 2 photograph from 1989, a gorgeous blue sphere marked by the Great Dark Spot, floating in the void of the outer solar system. That image shaped a generation of planetary science. It made Neptune look serene, distant, and fundamentally simple, a blue world far from the sun, cold, quiet, nearly featureless compared to the dramatic banded atmospheres of Jupiter and Saturn. The fact that the Great Dark Spot vanished within 5 years, that new storms kept appearing and disappearing, that the winds were the fastest in the solar system, that the interior radiated more heat than the sun could provide. None of this displaced the iconic blue image from public consciousness. Neptune remained for most people the blue dot at the end of the diagram. Webb's observations have dismantled that image piece by piece. The blue is a visible light artifact of methane absorption. In the infrared, the planet is dark. The atmosphere is not calm. It is racked by supersonic winds, punctuated by rapidly evolving high-altitude storms, and wrapped in an equatorial circulation pattern visible only at infrared wavelengths. The rings, nearly invisible in most ground-based observations and forgotten by the public, stand out with crystalline clarity. Dust bands between the rings reveal ongoing microphysical processes operating in the ring plane. Triton, the moon most people could not name, outshines the planet that captured it and may harbour a subsurface ocean beneath its frozen, geyser-scarred surface. And the upper atmosphere, the ionosphere, carries the infrared glow of auroras powered by a magnetic field so tilted and displaced that the glow appears in places no one would predict without knowing the field geometry. Each of these revelations individually would be significant. Taken together, they constitute a transformation in how Neptune should be understood. This is not the static, featureless ice ball at the end of the solar system diagram. This is an active planetary system with a dark methane-absorbing atmosphere, vigorous cloud dynamics, maintained ring structures, a captured moon brighter than the planet itself, a shattered and rebuilt satellite family, and a magnetically driven auroral system that had been hiding in a cooling upper atmosphere for decades. The shift from visible light to infrared light did not just improve the resolution, it revealed categories of information that visible light observations simply cannot access. The thermal signature of equatorial circulation, the reflective contrast between nitrogen ice and methane haze, the dust band structure of the ring plane, the H3+ emission from the ionosphere. Each of these is an infrared phenomenon, invisible or nearly so in the wavelengths where human eyes and most earlier telescopes operate. Webb did not give us a sharper version of the old Neptune. It gave us a different Neptune, one that had been there all along, but that could only be seen with the right instrument. This has implications beyond Neptune itself. Every image of the outer solar system that we carry in our heads is a visible light image. The blue of Neptune, the banded cream and ochre of Jupiter, the gold of Saturn's cloud tops. These are the wavelengths where human vision evolved, and they have shaped our intuitive sense of what the planets look like. But the planets do not exist primarily in visible light. They radiate, absorb, reflect, and emit across the entire electromagnetic spectrum. The visible light portraits are a narrow slice of reality, a fraction of the information these worlds carry. Webb's infrared view of Neptune demonstrates that switching wavelength ranges does not just adjust the contrast. It can reveal an entirely different planet, hiding behind the familiar one. The 2022 ring and cloud images drew global media attention when they were released. They became one of the early iconic images of the Webb mission, shared millions of times, printed in newspapers, projected on screens at science conferences. But at the time, the Aurora discovery had not yet happened. The images were received as beautiful, as impressive, as a reminder that the outer solar system still has surprises. They were not yet understood as part of a larger pattern. Now, seen in the context of the 2025 auroral detection, the 2022 images carry a different weight. They were the first act of a systematic revelation. Webb was not simply taking sharper pictures of a known planet. It was exposing layer after layer of hidden activity on a world that the scientific community had, with some justification, largely set aside for decades. No dedicated mission had been sent. No orbiter had been planned. The Voyager 2, data from 1989, remained the primary resource for virtually every aspect of Neptune science. And those data were collected in hours, by a spacecraft that never slowed down, during a flyby that was never repeated. Webb arrived and, in two sets of observations separated by a year, demonstrated that Neptune is not a world that can be understood from a single flyby snapshot taken 35 years ago. The atmosphere has changed. The upper atmosphere has cooled dramatically. The auroras were invisible to every instrument that tried before. The rings and dust bands had not been seen in the infrared until Webb looked. The Moon system carries a history of capture and destruction that ground-based observations can only partially reconstruct. This planet has been evolving, changing, operating as a complex system all along, and we have been watching it through a keyhole. The full picture that emerges from Webb's Neptune observations to date is not comfortable. It is the picture of a planet we have been underestimating, a world complex enough to demand sustained, dedicated study, receiving instead a handful of telescope observations spaced years apart and a single flyby conducted before the fall of the Berlin Wall. The instruments Webb used to reveal Neptune's hidden layers, the near-infrared camera and the near-infrared spectrograph, are general-purpose instruments serving thousands of competing science programs across all of astronomy. Neptune must wait its turn alongside distant galaxies, exoplanet atmospheres, star-forming regions, and black hole environments. Every observation of Neptune is a hard-won allocation of the most oversubscribed telescope in the history of astronomy. And yet, every time Webb has looked at Neptune, it has found something that changes the story. The rings came back, the dust bands appeared, the atmosphere went dark, the clouds blazed, Triton outshone everything. The auroras revealed themselves. The thermosphere had cooled by half. None of this was predicted. None of it was expected at the level of detail and surprise that the observations delivered. The question that now hangs over the entire Neptune system is not what Webb might see next. It is whether we are prepared to act on what it has already shown. The rings demand compositional analysis that only an orbiter can provide. The auroras demand sustained monitoring that a single telescope shared among thousands of programs cannot deliver. The Moon system demands close-range imaging and spectroscopy that no Earth-based or Sun-orbiting instrument can achieve. Triton demands a mission of its own, a world with nitrogen geysers, a possible subsurface ocean, and a surface unlike anything in the inner solar system, visited once for a few hours and never again. Everything Webb has revealed about Neptune points in the same direction, toward the realization that the most distant major planet in our solar system has been hiding a complex, active, evolving system beneath an appearance of cold simplicity, and toward the uncomfortable recognition that, despite everything we have learned in the past 4 years, we have barely begun to understand what is happening out there. The story now steps back even further, past Neptune's rings and auroras, past its tilted magnetic field and cooling atmosphere, to the question that connects this single ice giant to the rest of the galaxy. Because Neptune is not just one strange planet at the edge of our solar system, it belongs to a class of worlds that turns out to be one of the most common types of planet in the universe, and we know almost nothing about them. There is a category of planet in our galaxy that is more common than any other large world astronomers have found, more common than gas giants like Jupiter and Saturn, more common than rocky super-Earths hugging close to their parent stars. When the Kepler Space Telescope surveyed hundreds of thousands of stars and catalogued the planets transiting across their faces, a pattern emerged that nobody had anticipated. The most frequently occurring type of planet with a radius between roughly 2 and 4 times Earth's was the ice giant. Worlds approximately the size of Neptune and Uranus appeared again and again in the data, orbiting stars across the Milky Way at a wide range of distances. They were not rare curiosities. They were, statistically, among the most typical outcomes of planet formation in the galaxy. This makes Neptune and Uranus extraordinarily important. They are our local representatives of the most common class of large planet in the known universe. They are the only ice giants close enough to study in any detail. They are the testbed against which every model of ice giant formation, composition, atmospheric dynamics, magnetic field generation, and moon system architecture must be calibrated. If we want to understand what the billions of ice giant exoplanets orbiting distant stars are made of, how they behave, how their atmospheres circulate, how their magnetic fields interact with stellar winds, we need to understand our own ice giants first. And we barely do. The sum total of close-range data collected from Neptune and Uranus comes from a single spacecraft. Voyager 2 flew past Uranus in January of 1986 and past Neptune in August of 1989. Each encounter lasted hours. Its instruments predated the personal computer era, engineered not for sustained study of any single world, but for rapid reconnaissance during a once-in-a-century planetary alignment that allowed a single trajectory to visit all 4 giant planets. Voyager 2 was never intended to be a dedicated ice giant mission. It was a grand tour flyby spacecraft, moving at tens of thousands of kilometers per hour, gathering as much data as it could in the brief window where each planet filled its instrument's field of view. And then it was gone. Outward, away, into the heliosheath and eventually into interstellar space, still transmitting but never to return. That was 37 years ago for Neptune, nearly 4 decades. In that time we have sent orbiters to Jupiter, Saturn, Mars, Mercury, Venus, and the Moon. We have landed rovers on Mars and probes on Triton. We have dispatched the Europa Clipper toward Jupiter's icy moon. We have built the most powerful space telescope in history and pointed it at objects 13 billion light-years away. But we have not gone back to Neptune, and we have not gone back to Uranus, the 2 ice giants of our solar system. The only local examples of the galaxy's most common large planet type have been studied from close range for a combined total of roughly 1 day of flyby data collected with 1970s-era instruments. Everything else we know comes from ground-based observations, Hubble and now Webb, all of which are limited by distance, resolution, and the fundamental constraint that you cannot orbit a planet 4.5 billion kilometers away with a telescope sitting near Earth. The contrast with the gas giants is stark. Jupiter has been visited by 9 spacecraft and orbited by 2, Galileo and Juno. Cassini spent 13 years orbiting Saturn, deploying the Huygens probe to the surface of Triton. These missions generated datasets so rich that scientists are still mining them decades later. The understanding of gas giant atmospheric dynamics, magnetospheric physics, ring structure, and moon geology that emerged from these orbital missions is orders of magnitude deeper than what a flyby can provide. And yet the ice giants, which may hold the key to understanding the most common type of large planet in the galaxy, have received nothing comparable, not even close. This gap is not an oversight born of indifference. It is a consequence of distance, cost, travel time, and the brutal mathematics of orbital mechanics. Neptune orbits 30 astronomical units from the Sun. A spacecraft travelling with conventional chemical propulsion and using a Jupiter gravity assist to accelerate toward the outer solar system would require roughly 12 to 14 years to reach Neptune. A Uranus mission with similar trajectory design would take about 13 years from launch to orbit insertion. These are generational timescales. A principal investigator who begins working on a Neptune mission proposal today may not see the spacecraft arrive until they are near retirement. The missions compete for funding against faster turnaround projects with shorter feedback loops, and the launch windows are constrained by planetary alignments. Optimal opportunities for reaching the ice giants using Jupiter gravity assists occur in narrow windows, and the next favourable windows for both Uranus and Neptune fall in the early 2030s. In 2022, the planetary science community completed the Decadal Survey, covering priorities for 2023 through 2032. This document, produced by the National Academies of Sciences, Engineering and Medicine, represents the consensus recommendation of hundreds of planetary scientists about where NASA should focus its flagship mission investments for the next decade. The top priority flagship mission recommended by the survey was the Uranus orbiter and probe, not a flyby. An orbiter, designed to spend years in the Uranian system, studying the planet's atmosphere, interior, magnetic field, rings, and moons in sustained detail. The mission would also deploy an atmospheric entry probe to directly sample the composition of Uranus's atmosphere for the first time, measuring noble gas abundances and isotope ratios that encode information about where and how the planet formed. The Uranus orbiter was selected over a competing Neptune mission concept called Neptune Odyssey, which would have been a Cassini-class orbiter targeting the Neptune-Triton system. The selection was driven primarily by logistical and cost considerations rather than scientific priority. Both ice giants are considered equally compelling scientific targets. Each has things to teach that the other cannot. But a Uranus mission is slightly easier to execute. The travel time is shorter. The orbital insertion is less demanding. The available launch windows are more favourable. And the Decadal Survey can only recommend a limited number of flagship missions given the realities of the federal budget. Neptune Odyssey remains on the shelf. It has been studied in detail, The mission design exists. The science case is written. If funded, it could launch in the early 2030s, use a Jupiter gravity assist, and arrive at Neptune in the mid-2040s, roughly 55 years after Voyager 2's departure. The spacecraft would carry a camera, a magnetometer, a mass spectrometer, dust sensors, a radio science system, and an atmospheric probe. It would orbit Neptune for years, executing repeated flybys of Triton, mapping the ring system, monitoring atmospheric changes, and characterizing the magnetosphere that Webb has now shown produces auroras at mid-latitudes powered by a magnetic field unlike any we have studied up close. Meanwhile, Chinese scientists have proposed an independent Neptune orbiter targeting a 2033 launch. If both the American Uranus mission and the Chinese Neptune mission proceed, the 2040s could see the first simultaneous exploration of both ice giants, enabling real-time comparative planetology between the two most neglected major worlds in our solar system. But none of these missions exist yet. They are proposals, studies, recommendations, aspirations. Funding must be allocated. Hardware must be designed and built. Launch vehicles must be secured. Political support must be maintained across administrations that change every 4 or 8 years, while the missions require 20 or more years from inception to data return. The history of planetary exploration is littered with missions that were studied, recommended, and then deferred indefinitely because priorities shifted, budgets contracted, or timelines stretched beyond institutional patience. This is the context in which Webb's Neptune observations carry their deepest significance. Webb is not a Neptune mission. It is a general-purpose observatory, serving the entire astronomical community across all subdisciplines. Neptune must compete for telescope time against exoplanet atmospheres, high-redshift galaxies, star-forming regions, black holes, and every other target in the observable universe. The observations that revealed Neptune's auroras in 2025 were obtained under a guaranteed time observation program, meaning they were allocated as part of the telescope's initial commitment to the scientists who built its instruments. Future Neptune observations are not guaranteed. They will depend on competitive proposal reviews, on whether the science case is judged strong enough, relative to all other proposed uses of the telescope's limited time. And yet the scientific case Webb has built for Neptune in just a handful of observations is extraordinary. Not one result confirmed what existing models predicted. Each one exposed a gap between what we assumed about this planet and what is actually happening there. The surprise was not any single finding, it was the pattern, that every time the telescope gathered light from Neptune, the data overturned a prior assumption. That pattern is the strongest possible argument for sustained observation and, ultimately, for a dedicated mission. H3+, the molecule that had been the auroral tracer for every other giant planet for 3 decades, was finally detected with a signal so strong that the lead author described being shocked by the clarity. Every one of these results argues for more observation. Every one of them raises questions that only sustained monitoring or close-range orbital investigation can answer. The Aurora discovery in particular has direct implications for mission design. Lee Fletcher, a co-author on the 2025 Nature Astronomy paper, stated it explicitly. As we look ahead and dream of future missions to Uranus and Neptune, we now know how important it will be to have instruments tuned to the wavelengths of infrared light to continue to study the auroras. This is not a vague aspiration, it is a concrete design requirement. A future Neptune orbiter must carry a near-infrared spectrograph capable of detecting and mapping H3+ emission across the planet's disk. It must be able to monitor how the auroral pattern changes with Neptune's rotation period of approximately 16 hours and with variations in the solar wind. It must be able to measure thermospheric temperatures repeatedly over months and years to track the cooling trend Webb discovered and to determine whether the trend continues, reverses, or oscillates with the solar cycle. The magnetic field itself demands orbital investigation. Voyager 2's magnetometer measured Neptune's field along a single trajectory through the magnetosphere. An orbiter would map the field from multiple positions, multiple altitudes, and multiple orientations, building a 3-dimensional model of the magnetosphere and its interaction with the solar wind. This model would reveal whether the field is primarily dipolar, as the Voyager 2 offset tilted dipole model assumes, or whether higher-order multipolar components are as significant as some analyses suggest. It would show how the magnetosphere reconfigures as Neptune rotates its tilted dipole through the solar wind every 16 hours. And it would provide ground truth for the superionic water dynamo models that laboratory experiments have only recently begun to constrain. Triton alone justifies a mission. This captured Kuiper Belt object is one of the most scientifically compelling moons in the solar system. It has active nitrogen geysers. It has a tenuous nitrogen atmosphere. Its surface shows terrain unlike anything seen elsewhere, including the cantaloupe-textured regions photographed by Voyager 2. Some models suggest Triton may harbour a subsurface ocean maintained by tidal heating from its interaction with Neptune's gravity. If liquid water persists beneath that frozen surface, the astrobiological implications are immediate, and yet we have no way to investigate them from Earth. And yet the only close-range data we have for Triton comes from a flyby that lasted hours, recorded by a spacecraft that had already been travelling for 12 years. The 2022 Webb image showed Triton outshining Neptune in the infrared. That image, beautiful as it was, is also a reminder of how little we know. We can measure Triton's reflectivity and infer its surface composition from afar. We cannot map its geology. We cannot sample its geyser plumes. We cannot determine whether a subsurface ocean exists. We cannot study its interaction with Neptune's magnetosphere, which is significant because Triton orbits within the magnetosphere and its tenuous atmosphere should be affected by magnetospheric particle bombardment. All of this requires being there, orbiting, observing at close range over extended periods, and we have not been there since August of 1989. The broader tragedy is not just that Neptune has been neglected. It is that the neglect distorts our understanding of planets as a category. When we build models of planetary formation and evolution, we calibrate them against the planets we know best. We have extensive data on gas giants from decades of orbital missions at Jupiter and Saturn. We have detailed knowledge of rocky planets from centuries of studying Earth and decades of robotic exploration of Mars, Venus, and Mercury. But for ice giants, the intermediate class that sits between gas giants and rocky worlds, our observational anchor is almost non-existent. 37-year-old flyby data from a single spacecraft. A handful of telescope observations from billions of kilometers away. And now, a few hours of Webb data that have already overturned assumptions about atmospheric temperature, auroral visibility, ring structure, and cloud dynamics. Every model of ice giant interiors relies on assumptions that have not been tested by close-range measurement. The interior structure of Neptune, the layering of hydrogen-helium envelope over water-ammonia-methane mantle over rocky core, is inferred from bulk density, gravitational harmonics measured during the Voyager 2 flyby, and theoretical equations of state for materials under extreme pressure. The superionic water hypothesis for the magnetic field dynamo is supported by laboratory experiments, but has not been confirmed by any measurement taken inside or near an ice giant. The atmospheric composition beyond the top few bars of pressure is almost entirely theoretical. We do not know the abundance of noble gases, the isotopic ratios of key elements, or the vertical mixing profile of the deep atmosphere. These measurements are exactly what an atmospheric entry probe would provide, and they are exactly what the Uranus orbiter and probe is designed to collect at Uranus. But Uranus is not Neptune. The two planets are similar in many ways. Both are ice giants. Both have tilted, offset magnetic fields. Both have ring systems. Both have moons, including moons that may be geologically active, but they are not identical. Neptune is denser than Uranus. Neptune radiates more internal heat than Uranus, more than twice as much energy as it receives from the Sun, while Uranus radiates almost no excess internal heat at all. This difference in internal energy output is one of the great unsolved puzzles in planetary science. It may relate to differences in interior structure, to differences in how the two planets formed or migrated, or to a catastrophic event in Uranus's past. Perhaps the giant impact thought to have tipped it on its side. Neptune's magnetic field, while similar in tilt to Uranus's, has different multipolar characteristics. Neptune's wind speeds are the highest measured on any planet, approaching 2,200 km per hour, while Uranus's winds are somewhat slower, Triton is a captured Kuiper Belt object with no counterpart in the Uranian system. The two ice giants are two different experiments in planet building, and understanding both is necessary to understand the class they represent. If only one is visited by a dedicated orbiter in the next several decades, the understanding we gain will be incomplete. It will tell us about one ice giant in detail, and leave the other as a point of comparison known only from a flyby and from telescopic observations. This is better than the current situation, where neither has been visited by an orbiter, but it is not enough. Not for a class of planet that outnumbers gas giants in our galaxy by a significant margin. Not when the formation and migration of ice giants played a critical role in shaping the architecture of our own solar system, scattering smaller bodies, sculpting the Kuiper Belt, and possibly influencing the delivery of water and organic molecules to the inner planets where life eventually arose. Webb's Neptune observations have landed at a pivotal moment. The decadal survey recommendation is fresh. The early 2030s launch windows are approaching. The technical capability to build and fly an ice giant orbiter exists. The scientific case, already strong before Webb looked at Neptune, has been dramatically strengthened by every result the telescope has returned. The Aurora discovery alone would justify adding infrared auroral mapping to the instrument suite of any future ice giant mission. The thermospheric cooling discovery alone would justify long-duration atmospheric monitoring. The ring observations alone would justify a dedicated ring science payload. Triton's brilliance in the infrared alone would justify a mission profile with extensive Triton flyby sequences. Whether the missions happen depends on decisions that will be made in the next few years. Budget negotiations, engineering reviews, launch vehicle availability, political will. The gap between a decadal survey recommendation and a spacecraft on a launch pad is filled with practical realities that have nothing to do with science and everything to do with funding, scheduling, and institutional momentum. Missions to the outer solar system require generational commitment. The scientists who advocate for them must accept that many will retire before the data arrive. The agencies that fund them must maintain support across administration changes and budget cycles that fluctuate unpredictably. The public that ultimately pays for them must be convinced that the investment is worthwhile, that understanding a planet 4.5 billion kilometers away matters to people standing on this one. Here is why it matters. Neptune is not a distant abstraction. It is a member of our planetary family, one of 8 major worlds that formed from the same disk of gas and dust that produced Earth. The processes that built Neptune, the accretion of ice and rock in the outer solar system, the capture of a hydrogen-helium envelope, the generation of a magnetic field by exotic high-pressure chemistry in the interior, are the same processes that built planets around billions of other stars across the galaxy. Understanding Neptune means understanding planet formation itself, not as a theoretical exercise, but as a set of physical facts constrained by measurement. And what Webb has revealed is that the physical facts are stranger than anyone assumed. A planet that can cool its upper atmosphere by hundreds of degrees in just decades. A magnetic field generated by a disordered lattice of superionic water that places auroras at latitudes where no familiar planetary model would put them. A ring system maintained by dynamical processes that have operated continuously since before life appeared on Earth. A captured moon larger than Pluto that destroyed and rebuilt the satellite system around the planet that captured it. Supersonic winds in an atmosphere so far from the Sun that noon resembles twilight on Earth. An ionosphere that glows with the fingerprint of H3+, the same molecule that traces auroral activity on every other giant planet, detected at last after 30 years of failure, because the atmosphere had quietly cooled below every prediction. None of this was visible from the vantage point of a single flyby in 1989. None of it was accessible until a telescope with the right sensitivity, the right wavelength range, and the right position beyond Earth's atmosphere looked at the right target at the right time. And even now, with Webb's extraordinary capabilities, every glimpse is partial. Brief observations, limited wavelength coverage, no ability to orbit, to sample, to probe. Every result is a glimpse through a closing window, because Webb's time is finite. The competition for that time is intense, and the telescope itself will not operate forever. The window is closing in another sense too. The early 2030s launch windows for ice giant missions using Jupiter gravity assists represent an alignment of orbital mechanics that does not repeat frequently. If those windows pass without a mission being ready to fly, the next favourable opportunities may not arrive for years or decades, adding corresponding delays to an already generational timeline. Every year of delay is a year of continued ignorance about a class of planet we know is common across the galaxy, but have barely studied in our own backyard. Neptune was never the planet people thought it was. It was never the cold, quiet, featureless blue world at the edge of the classroom diagram, the afterthought at the end of the solar system tour, the planet that could be summarized in a single sentence about methane and distance. Webb has proven that. In 2 sets of observations totaling mere hours of telescope time, it exposed a planet with hidden auroras, a dramatically cooling upper atmosphere, a magnetic field generated by exotic physics in a high-pressure interior, delicate rings and dust bands invisible in other wavelengths, vigorous high-altitude storms, a global circulation pattern etched in infrared light along the equator, and a captured moon that outshines the planet in the infrared and carries a geological history unlike anything in the inner solar system. Every one of those revelations was a surprise, not because the physics was unknown, but because the observations had never been made, the data had never been collected. The instrument capable of revealing these features had not existed until Webb reached its operating position, 1.5 million kilometers from Earth, and began looking at a planet that most people considered solved. Neptune was not solved, it was unexamined. There is a difference, and it is the difference that should haunt anyone who cares about how much we still do not know about the worlds we share this star with. The most distant major planet in the solar system was never silent. It was never still. It was never simple. It was glowing with auroral light in wavelengths we could not see, cooling its atmosphere for reasons we cannot explain, carrying rings we had forgotten, orbiting a magnetic axis that points in directions no textbook would predict, and holding a captured moon whose frozen surface reflects more light than the planet's own methane-darkened atmosphere. It was doing all of this every day, every year, every decade while we looked elsewhere. Webb did not discover a new Neptune. It discovered the Neptune that was always there, waiting in the infrared, waiting at the edge, waiting for an instrument sensitive enough to see what the cold and the distance and the darkness had been hiding. And the most unsettling part is not what Webb found. It is the certainty that it has only shown us the outermost layer of a world whose depths remain as unknown as they were the day Voyager 2 passed through and never came back.